Welcome to video lecture M6. This is our second one on matrix operations. I'll be your conductor, Tom Roby, and here are the outline and objectives. We'll memorize the definition of the transpose, written A upper right like an exponent, A exponent T of a matrix A, and compute examples. We'll generalize some algebraic properties of transpose for numbers to matrix multiplication and demonstrate that some others fail. And we'll apply properties of these operations and examples and as part of reasoning and proofs, although we may not get there in this video lecture particularly. So recall the definition of matrix multiplication from the previous lecture, where if we want to know what A times B is, we just take the first column of the product is going to be the B1 linear combination of the columns of A. The second column is the B2 linear combination of the columns of A, and so on. So each one is a linear combination of the columns of A, but the coefficients of the linear combination are taken by the columns of B1, right? And so also remember that if A is an m by n matrix and B is an n by p matrix, then we end up with an m by p matrix, right? And so it's like those two n's in the middle cancel. Okay. So here's a proposition that tells us some of the properties of this operation. And I guess the thing I want to stress with this case is if we're looking at something like we've got matrices of appropriate sizes. So that means that they all have to work so that the n's in the middle, that these two middle numbers match with one another when you're doing the multiplication. And r is just some real number, right? So what does this mean when I write ABC equals ABC, right? What do I mean? Well, it means if like I take the product of B and C first, that's the matrix, and then I multiply it by A. Do I get the same thing as if I multiply A and B together, get some other matrix and multiply that by C? And I think really the way you want to look at this is, let's see, we've got a bunch of blobs here, and I think in order to make this work, I need an r to the q first, and then I'm going to go to an r to the p, and then I'm going to go to r to the n, and then I'm going to go to r to the m. Okay? And so A was always my m by n matrix. B was always my n by p matrix. And now I've got a matrix C, which I guess is going to have to be p by q. Okay? So in order for these dimensions to work out, A has to be m by n, B has to be n by p, and C has to be p by q. But remember, when I'm multiplying them, I'm multiplying, even though I'm doing the operations in this order. Why is that? Well, because I want to think about them as applying to some vector x, right? So I take x, and it goes to cx, right? So let me just make sure that's clear that that's a cx. Usually I don't erase in the middle, but maybe this time I will. So this is cx, and now this is going to be bcx. And then finally I've got abcx. Okay, so that's these points here. And so this goes to this point, which goes to this point, which goes to this point. Okay? So what am I saying when I say, dudes, I want to have A times BC be the same as AB times C? Really what I'm saying is, suppose I want to go from Chicago to Philadelphia to Hartford to Boston. Right? Well, I could describe that as, depending on what cities I care about, I could say, well, if I combine the B and the C together, then I've really just gone from Chicago to Hartford and followed that by Hartford to Boston. Right? So this combination represents BC thought of as one transformation followed by A. Okay? Now the other way I could think about this is let's see, I've used that color. So now instead of doing that, I could do C, right? Just go one hop. And then I could do this as two hops. So I go from Chicago to Philadelphia, and then I go to Boston, and I don't pay any attention to the fact that Hartford was along the way. Okay? So that's really why these guys are true, because when we compose functions, when we write the composition of two functions, we're really just kind of compressing two operations into a single operation. Okay? And so whether you compress these two operations together and then do that, or compress these two operations and do this first, as long as you keep the order the same, A, B, C, notice these always come in the same order, then it'll be true. So that's why this is called the associative property, and it's the property that actually is maybe the hardest one to show. If you were just using like a row-column definition of this, you would find yourself really up a creek trying to prove something like this. Okay, what else do I want to say about these properties? The fact that A times B plus C is AB plus BC, well, think about it, right? B plus C just means that instead of having each of these columns would be the column B1 plus C1, B2 plus C2, and so on, BP plus CP, right? And so we know that A for matrix vector multiplication, that we have the distributive property. And so the fact that we're just concatenating these things mean that this property generalizes from matrix vector multiplication to matrix-matrix multiplication. And the same thing for 3. So those guys are really easy to see from this point of view. And similarly 4, same kind of idea, right? What does it mean when I multiply a matrix B by R? Well, that means I multiply every entry in it by R. So that means that each of these B's is just going to be the same column vector except rescaled by R. Every entry is going to be rescaled by R. Well, that means, okay, what does that mean? That means that then when I take this R rescaled linear combination, I'm just going to be rescaling everything in each of these column vectors by R. And so at the end of the day, every entry in AB has been rescaled exactly by R. So that shows that A times RB is the same as R times AB. And a similar thing would apply if you looked at the one in the middle. All right, so now I guess I should remind you, what is I sub m? It's not instant messenger, which is probably something that is long gone, some technology that's long gone. But I sub m is the m by n identity matrix. So it's an identity matrices are always squared. Right, so this is basically 1, 0, 0, 0, 1, 0, 0, 0, 1, or maybe it's bigger in certain dimensions, but this is the 3 by 3 identity matrix. And so A, of course, is going to be the usual like m by n matrix, so I can multiply it by an m by n matrix on the left, and I'll get it back A. Or I can multiply it by an n by n matrix on the right, and I'll get A. So the idea, just to write a concrete example here, is that if I've got a matrix like 1, 2, 3, 4, 5, 6, this is a 2 by 3 matrix. Well, I could multiply it by I2, 1, 0, 0, 1, right? So this is I2. If I multiply I2 times this, then I'll just get back the same thing I started with, right? So this is equal to 1, 2, 3, 4, 5, 6. Or, now if I'm going to do something on the other side, 1, 2, 3, 4, 5, 6, now I've got a 2 by 3 matrix. If I'm multiplying it on the right, I have to multiply it by a 3 by 3 identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And I'll still get the same thing. Now, if the matrix A I start with happens to be square, then I'd be multiplying by the same dimension. Instead of having I2 here and I3 here, I'd say have I3 on both sides. So in that situation, I could say that the matrices actually commute. It's true that I can multiply them in either order and I get the same thing. But here's something that's not part of the proposition, but is maybe more important, which is the idea that matrix multiplication does not commute often. Okay? In fact, you know, what does it even mean necessarily, right? If multiplying B to A means going from R to P to R to the N to R to the M, then multiplying by A, B would go from R to the N to R to the M to R to the P, maybe, but maybe the dimensions wouldn't match. Let's take a look at an example. So let's think about the dimensions of AB versus BA. So if I have something like 1, 2, 3, 4, 5, 6, right? I can multiply it by this on the left, but I can't multiply by I2 on the right because the dimensions don't work out. So sometimes AB is defined, but BA is not, because I can't switch these. I have to, if I want to multiply by an identity matrix on the right, I have to multiply by the 3 by 3 identity matrix. So you can see that just dimension out from a standpoint of dimensions that things don't always work. On the other hand, you could say, well, okay, let's make them all square matrices, right? Because square matrices, you never get into any problems with dimensions. Then basically you can think about it, if you've got square matrices, then you're sort of like saying, okay, what have I got? I've got r to the n here. So if you have an n by n matrix, you've got r to the n, and you're mapping it to r to the n. And of course, you can either think about it this way, you could think about taking r to the n to itself, and so you can just think about repeating that over and over again. So then you don't have any problem if you have two matrices, you know, A and B, from r to the n to r to the n, then you could multiply them in either order. But here's the thing, is that most of the time, it's only special cases where you can count on them being the same. All right, how about a to the fourth? Can we make sense of a to the fourth? Well, so what does that mean? So a takes r to the n to r to the n. We can only make sense of a to the fourth if it's a square matrix. Okay? So if it's a square matrix, if you have an m by n matrix, and then you want to multiply it by another m by n matrix, that only works if n and m are equal. Okay? So you can make sense of a to the fourth as long as it's a square matrix. So many things work for square matrices that don't work in general. So here's another question. We know that for real numbers, if you take a product of two real numbers and you get 0, then one of those two numbers has to be 0. Do you think that's true for matrices? Well, if you thought no, then you're correct. It's actually quite possible to come up with examples of two matrices whose product is 0, but neither one is 0. In fact, you should be able to even come up with an example of two matrices where none of the entries in either of those matrices is 0, but you can still make their product be 0. And so that's a challenge for you. Just in the 2 by 2 case, you can do this. You don't need anything very fancy. All right, here's another thing. Suppose, you know, in the real numbers, if you have AC equals BC and C is not equal to 0, then you can cancel, right? And you could do that on the left or on the right. Then A equals B. Would that be true for matrices? Answer again is no, and even for 2 by 2 matrices you can see that. And in fact, these two statements are actually very closely tied to one another, and you can use examples for one to generate examples for the other and show that, you know, if one holds, then the other one probably has to hold. So here's your exercise, right? Find examples of matrices, just 2 by 2 matrices. That's what I mean by r to the 2 by 2. 2 by 2 matrices with entries in r, such that they don't commute with each other, or another pair where their product is 0, but neither A nor B is 0. In fact, maybe they don't have any 0 entries even. And finally, something that violates the cancellation law. So you need to find A, B, and C such that that's true. Okay, and so if you can do that, then you'll really understand a lot of what's going on with the algebra of matrices and how it's different from most of the algebraic structures that you've been exposed to in the past. Okay, so the last topic for this video lecture is matrix transposes. So this is a very nice operation. It's very simple to understand. If you have an m by n matrix A, then the transpose of the matrix is the n by m matrix. So you flip the dimensions, whose rows are the columns of A. Another way of thinking about that is if A is Aij, then a transpose is Aji. So let me show you a quick example just to make sense out of that. So I take the transpose of the matrix whose rows are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I get the matrix whose columns are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which I might read as 1, 5, 9, 2, 6, 10, 3, 7, 11, and 4, 8, 12. Okay? So notice that I've converted, takes a 3 by 4 matrix and makes it a 4 by 3 matrix. Now, it could be that your matrix is square. We often want to think about specialized to the square matrix case. And in that case, well, what have you done? You've taken A, B, C, D, E, F, G, H, J and turned it into A, D, G going across B, E, H, C, F, J. Okay, so you just interchange rows and columns. And if you want, you can think about, okay, in the transpose, say the 1, 2 entry of the transpose is 5. Well, that was the 2, 1 entry of this. So that's what this definition means. Sometimes thinking about it that way is helpful for if you need to write out a proof of some simple fact. So here's the proposition. The first thing to state is, what happens if you apply the transpose twice? Well, it's pretty clear you get back where you started, right? All you're really doing is taking this matrix, kind of flipping it in some sense, right? Flipping it diagonally, right? So if you flip it diagonally twice, you end up back where you started. You replace the rows with the columns. It's the same thing as replacing the columns with the rows. Okay, so here's another property. If I take the sum of two matrices and I take their transpose, then that's the sum of the transposes. Okay, so that's really easy to see too, right? Because if I had, two matrices like this, and I added them, then I'd just be adding them component-wise, right? And then I take the transpose. But I could have taken the transposes and added them, and the components would still be in the corresponding places. Okay, so there's nothing very exciting or deep about that. If you didn't see it from my vague hand waving, you'll see it when you write out an example. Okay? Similarly, if you rescale a matrix and then take its transpose, well, then you're just going to be take the transpose and rescale. All you've really done, it'd be like taking every entry here and doubling it, then take the transpose. Well, every entry would be doubled, right? So that's all that's going on there. And finally, here's something that you should be a little bit careful about, right? If I take the transpose of a product of two matrices, you might want it to be A transpose B transpose. But it's not. It's B transpose A transpose. So the things happen in the other order. It's not equal to A transpose B transpose. And so that's the one that I think you should think about the hardest and see if you can figure out why that makes some sense, right? Maybe it's not quite so easy to see, but even if you think about the dimensions, you'll see that A transpose B transpose wouldn't work. Now, of course, if they're square, then that doesn't tell you anything. But you should try to come up with some 2x2 examples where this fails. So here's your last exercise from this video lecture, which is to find an example of two 2x2 matrices A and B so that AB transpose is not equal to A transpose B transpose. And that's it for this video lecture. Thank you for your kind attention.